Welcome back. You're back for more. I don't blame you. This is the most important thing that you could be doing. This is question 1. This equilibrium stuff is going to be question 1 of the free response the minute you have finished your multiple choice section and you have cracked open your test booklet in the free response with your beloved calculator in your hand. I hope yours is pink like mine, but fellas, I understand. You know, blue's just as good. So, in any event, my name is Renee McCormick. I'm with the National Math and Science Initiative, and again, once again, happy that you are here. So, this is part 2 of working through AP problems. Hopefully, you've already listened to the AP essays in equilibrium, because that's where a lot of the multiple choice points are going to reside. What we do in the free response is question 1. There's no need to test it in multiple choice because you're going to have an equilibrium problem. The question is it going to be a gas law equilibrium, a concentration equilibrium, an acid-base equilibrium, or a solubility equilibrium? So let's see how they kind of warped this one. I see a graph. That's unusual. You normally don't see one of those on here. So let's look. We have an equilibrium established between 2 moles of HI and H2 plus I2. So we have a change in the number of moles equal to 0. We know that for sure. We don't have anything tricky like any solids or liquids thrown in to take us off course. Let's see what's going on. After a 1 mole sample, well, that's nice, a 1 mole sample of HI is placed into an evacuated 1 liter container, well, that makes the math easier, at 700 K. Keep your eye on the temperature. The reaction represented above occurs. The concentration of HI as a function of time is shown below. Write the expressions for the equilibrium constant Kc for the reaction. Well, all right, that doesn't really have anything to do with the graph, but I can do that. So Kc is equal to, and they want the C, so they're talking concentrations, so square brackets are appropriate here. H2, I2 over HI, where the square brackets represent concentration in moles per liter. Don't forget to square it because of that 2 sitting right there. All right, so as we look at this graph, just again from a multiple choice point of view, right there is the time at which equilibrium occurs, right when that flat line happens. That's when the rate of the forward is equal to the rate of the reverse. So they have given us essentially the rate of the forward. And part B says, what is the concentration of HI at equilibrium? Well, read the graph. Wow, that's an easy question. The concentration of HI is equal to 0.80 molar, taken directly off the graph. All right, now determine the equilibrium concentrations of H2 and I2. Okay, well, now we're getting somewhere, because that so far has just been what I call kind of the pity points, the things that are super easy in an equilibrium question, because they know that you're nervous. You're nervous because you're starting the second half of the test. So often you should come to expect a couple of things. Number 1, not everything on this test is hard. Number 2, let the question lead you. It's leading me to a logical problem-solving technique. So they had me first get what the equilibrium concentration is of HI, and now they're asking me the equilibrium concentrations of the other players in this equilibrium. So break out a rice table if you need to. You do not have to do a rice table. If you can go straight to the fact that K is equal to the relationship they had us write up here and plug and chug things in, you don't have to do this. I only do this for those of you who may still be struggling and not getting the concepts. If you get it and you don't need it, by all means, do not waste valuable time doing a rice table. Initially, I had a mole, or actually 1 molar, because it was 1 mole in 1 liter. None and none. Change is minus x, plus x, and plus x. And at equilibrium, in terms of x, 1 minus x, I'm just adding the I and C lines together. So 1 plus a minus x is 1 minus x. 0 plus x is x, and 0 plus x is x. Now then, I can actually do some solving here. At equilibrium, they just had me solve for the fact that this was 0.80 molar. Well, therefore, x is equal to the difference between 1 and 0.8, which is really equal to 2x, right? I should put 2 right there. I'm so sorry. I left that out. Saw that little coefficient up there. I almost messed you up. So 2x is equal to that difference, so x is equal to 0.1. All right, so that means that concentration of H2, which is equal to the concentration of I2, is equal to 0.10 molar. There's my answer. Nicely boxed. Should have boxed it up here too. All right, then what do they want me to do? On the graph above, make a sketch that shows how the concentration of H2 changes as a function of time. So what is it at equilibrium? It is 0.1. We just solved for that. 0.1 would be right here. Notice that I'm using the exact same time of equilibrium, TEQ. And what I need to do is realize that initially I didn't have any of this stuff, because go back and read 1 mole sample placed into an evacuated container. There was nothing. So I'm going to start here at nothing, the origin, and I'm going to curve. And it's going to be tough because they didn't give me a lot of room to curve. I'm going to curve up to that point, and then flatline it. I'm going to do this. You didn't have to do that, but I just want it to be clear in case I've got to do something else with this. So easy enough. I got that done. All right, then what? Calculate the value of the following equilibrium constants at 700 K. Rearranging my paper a little bit here. Okay, so let's do Kc first, since that's what they want. And blue's good. So Kc is going to be equal to the concentration of H2, concentration of I2, over the concentration of Hi. Where am I getting all that? That's products over reactants from the balanced equation that they gave me. Again, don't forget that too. And that's equal to what we just found. Let the problem lead you. 0.10 for each of these, so I can just call that squared, over 0.8, also squared because of this 2. This 2 right here is because it's the same number times itself. All right, so 0.1 x squared divided by 0.8 x squared. And I come out with 0.0156. How many sig figs do I need here? 700 has 3. But some of the other numbers they've given me are 2. 1.0 mole, 1.0 liter. I'm going with 2. So let's call that 0.016. And it's naked. Relish the fact it's naked. Now, go back to your balanced equation. We already said that the change in the number of moles is 0. 2 moles on the left, 2 moles on the right. So Kp equals Kc. So Kp, I'll do it in a different color. Kp equals Kc RT to the delta N. And delta N equals 0 for this problem. Therefore, Kp equals Kc equals 0.016. Easy enough. And then finally, at 1000 K, where were we? That was 700. Yup, got to keep an eye on the temperature with these problems. At 1000 K, the value for Kc of the reaction is 2.6 times 10 to the minus 2, as opposed to 0.016, which is 1.6 times 10 to the minus 2. Okay, so we heat this puppy up, and it makes more product. In an experiment, 0.75 moles of Hi and 0.1 moles of H2 and 0.5 moles of I2, oh, they just gave me everybody. That means I got to calculate Q, and I got to compare Q to K, and I got to figure out which way the shift goes. To reach equilibrium at 1000, determine whether the equilibrium concentration of Hi will be greater than, equal to, or less than the initial concentration of Hi, and justify your answer. Okay, off with the Q. Q equals, again, H2, I2, concentration Hi, don't forget to square it, equals. Start plugging them in. 0.10. How did I get that? It's right here. 0.10. What's I2? 0.50. And what's Hi? 0.75. All right, clear my screen. 0.1 times 0.5, be 0.05, divided by 0.75, quantity squared. And I get 8.9 times 10 to the minus 2, I'm going to keep it in this notation since that's what they gave me as K. So now I need to compare. And we've been practicing this technique. I love it. Thanks again to the teacher in Virginia who taught me to do this summer. I like putting them in alphabetical order, K versus Q. And now think about the numbers. Q we just figured out was 8.9 times 10 to the minus 2. You don't have to do it this way. You don't have to write it this way. I'm just doing it for visual effect for you. I still think you're in the learning phase here. And K, they told us, was 2.6 times 10 to the minus 2. Well, they're both times 10 to the minus 2, and 2.6 is less than. So the arrow points to less than, and that's also the direction that the equilibrium is going to shift. So what do you really want to know? Determine whether the equilibrium concentration of HI, which was my reactant, go back to the top, confirm, yes, the reaction shifts that way, then isn't its concentration going to increase? So determine whether the equilibrium concentration of HI will be greater than, less than, or equal to that of the original. So Q, or I should say KC, is less than QC. So therefore shifts toward reactants. And I can also show it by the arrow. Therefore the concentration of HI must increase. Now, let's talk scoring. This was a 10-pointer. It was also the B exam, which means not as many kids took it. The kids crossed the international date line. 4.17 was the mean. So if you worked this out and you got 5 or more points, you are doing fine. All right, so I got a point for this. I got... this was interesting. Okay, on the graph, so I'm skipping around. I'm going to do the graph while I'm at this part of my screen here. For this little line business, I got 1 point for 2 of the following things, starting at 0, 0, and increasing to 0.1. So I got a point for this piece of the graph. And then I got a point for realizing that the time had to be identical for both of these. So I got a point for leveling off at that exact moment in time. All right, and then I got a point from being able to read the graph. And then I got a point each for those. I thought that was kind of a gift. 2 for my money there. I got a point for calculating this. Should have boxed it. That is consistent with whatever you have above. So you could have screwed up above, but if you put your numbers in this expression, did the math properly, you get this point, even if your answer is oh so wrong. And then I get a point for this value with verification. And verification comes in that format, explaining to the person who's grading your paper, hey, I know what you're doing to me here. You're doing the politically correct equation, PC. So KP equals KC RT delta N. Delta N is 0, therefore this becomes a big fat 1, and KP equals KC, and off you go. They're equal. Just don't forget to answer the real question, which was what was its value. And then finally, for that last part, you got a point for calculating Q and comparing it to KC. So getting this number and comparing it was worth a point, and then a point for the correct prediction. Now, another way to do this is to just look at the actual math of the situation, I guess, for lack of a better phrase. If the numerator is going to increase, then the denominator has to decrease. That's another way that you can explain this once you've written out the Q expression. Because they were 0.1, 0.1, and 0.8, which 0.75 is really close to that. So you could have done it that way as well. All right. We've only got 2 more to go. How does that feel? All right, make that bigger. Make this bigger. Kind of fuzzy. Sorry about that. Sometimes they come in clear and sometimes they do not. I cannot explain why. All right, another 10-pointer. You can pretty much bet that this question is always going to be 9 or 10 points. All right, so now what? Answer the following questions regarding the decomposition of arsenic pentafluoride, ASF5, A 55.8 gram sample, might need that, is introduced into an evacuated, that means nothing else is in there, so my rice table 0, 0 going on the reactant side, and that's a volume. And then here's a temperature, but you know what? You're not going to leave it that way. 273 plus 105, 378. If you get a V and a T and a pressure and a thing that could get you moles, I gotta feel there's a Pivnert moment coming on. So indeed, they so far have just told me 55.8 gram sample, introduced evacuated container, no volume, at a temperature that I converted to Kelvin, even though I didn't put the K on there. So what is the initial molar concentration? Well, that's moles per liter, so let's find the moles. So molarity is equal to grams over molar mass, because that's moles, over liters. Volume in liters, I should say. I'll put an L that way. And so 55.8 grams divided by, now you got to go get that molar mass. But you've already worked this problem, so hopefully you got the correct molar mass. When you take the mass of arsenic plus 5 times the mass of fluorine, you should come out with 169.9 or 170 if you wish. And then that is going to be divided by that volume of 10.5 liters. And you see that the grams cancel, and a 1 over a mole is mole, moles per liter. Okay, it's worth firing up the calculator now. So 55.8 divided by 169.9. That's my numerator, and that's my number of moles. I'm going to go ahead and write it down because I know that sometimes I wish I would. I've been tricked before, and that they need that. Like I may need that moles for something else, like a Pivnert in a minute. All right, so divided by the 10.5 liters gives me a molarity of 0.0, how many sig figs? 3 it is. 313. What's the initial pressure in atmospheres? See, yeah, can feel that Pivnert coming on. PV equals nRT. Therefore, solve for P, which is nRT over V. So, see, now I'm glad I did it. 0.328. I've been burned before, like I said. I'm just going to put R, and you can too. And the temperature is 378 Kelvin. Can't tell you how many kids would just put in that 105 degrees Celsius and think that was going to work. And 10.5 liters. Therefore, P equals. Now, hopefully you have R stored in your calculator. If you do not, you go 0.0821. And you hit store. And you store it as, well, R. So alpha, and above the multiplication sign is the R. You hit enter to make it stick, and there you go. So now all of that needs to be done. You need to have all of these sorts of constants in your calculator before you take the AP exam. We can't clear your calculator. If anybody tries to clear your calculator, you politely protest. And if that doesn't work, you send the fastest kid in the room down to get your teacher to come and set that proctor straight to say, no way, no how can you clear my kids' calculators. I had this happen to me once. Can you tell? I'm still a little bitter. All right, so now 0.328 times alpha R times 378 will get me my numerator, divided by 10.5, and I come out with almost an atmosphere. I'm going to stick with 3 sig figs. 0.969 atmospheres. Don't leave it naked. Alright, so far, I ain't done a dad-blasted thing with equilibrium. And this is how a lot of these start off. It's for the students who have just opened their test booklet. They can earn some points right away, even if they've never seen an equilibrium problem in their life. I call them the pity points, and I mean it respectfully. Take advantage of the pity points. So far, there have been 4 of them. 2 up top, 1 for getting the molar mass. Good grief. And 1 for translating that into a molarity properly. And then 1 point for subs, that you substituted things in right, and then 1 point for the final answer. Okay, maybe we'll get to some equilibrium in this part. At 105 degrees Celsius, staying at the same temperature, ASF5 decomposes into ASF3 and F2 according to the following chemical equation. See those adorable little double arrows? Now you should also realize that that means that delta N, should I need it, because when everyone's in a gas, while I'm there, I just think about it. 1 mole of gas on the left, 2 moles of gas on the right, that's an increase of 1, so that delta N is a plus 1. So in terms of molar concentrations, write the equilibrium constant expression for the decomposition. So when they say molar concentrations, that means Kc. So use the appropriate symbols for this. Products over reactants, everyone raised to the power of their coefficients. In this case, all are 1s, so that makes my life easier. So there you go. You get a point for that. So you got 5 points, and you haven't had to do very much with the equilibrium at all. Stick with purple. All right. Calculate the molar concentration of ASF5 at equilibrium. Oh, let me read the hints first. When equilibrium is established, 27.7% of the original number of moles of ASF5 have decomposed. Calculate the molar concentration. That's code for molarity at equilibrium. All right, so there's 2 ways to look at this. I'm going to look at it this way. 100% has minus what's decomposed gives me what's left. Can see this decomposed bit over here? So minus the 27.7% decomposed equals what's left at equilibrium. You don't have to write that. This is just my thought process. So 100 minus 27.7, you could do in your head, is 72.3. So therefore, 72.723 times the original number of moles. I know it was little, 0.0313, way back. Wait, that's molarity. Am I in concentration? I'm in concentration. Nope, they want moles. So I need the moles, 0.328. So divide by 100 to get it into that decimal form of 0.723, multiply it by 0.328, and I come out with 0.237. Oh, no. That said moles. This says molarity. That's not the number I want. That's not the number I want. I want the molarity. Sorry about that. I want this number, 0.0313. Read the question, McCormick. All right, so let's try that again. 0.723 times 0.0313. There it is. 0.022, what do you call that? 7. Molar remains. Should put a 0 there for good form. I'm bad about that. All right, using molar concentrations, calculate the value of the equilibrium constant, KEQ, at 105 degrees Celsius. At least they're staying with that same temperature. So now comes a moment of truth. You've worked enough of these that you probably already know how to set this up, right? Oop, that was a bit extreme. Sorry. Don't mean to make you dizzy. Calculate the value of the equilibrium constant. Okay, we just were led to coming up with AS5s, right? So we just got that. So what did we start with? We started with this 0.0313. So we know how much is gone. So we need to just simply calculate. So you can do a rice table, or you can cut to the chase. It's your call. I'm going to do the rice table because I'm just going to keep doing them until you get really good at them. But for those of you that get it,
you've done enough for homework, you've listened enough, you just understand what to do for my next expression down there at the bottom, you can go for it. ASF5 in equilibrium with ASF3 and F2. Initially, this was 0.0313. They made us calculate that way, way, way back up in Part A. I think it was Part A. Some of that's going to be gone. This is all one-to-one stoic, so for every x I lose, I make one each of the products. So E in terms of x is 0.0313 minus x. 0 plus x is x, and 0 plus x is x. So E is what I'm in search of. X is what I'm in search of. So therefore, KEQ is equal to the expression that we wrote earlier, which is the ASF3 and the F times F2 over ASF5. I'm just going to plug those in. So that's going to be, oh, I know E, for this one at least. What's the difference between 0.0227 and 0.0313? That difference is our x. So 0.0313 minus what's sitting in my calculator at this very moment is what x equals. So therefore, x equals 0.00867 for each of those. So KEQ is equal to 0.00867 quantity squared. In other words, x times x, x squared, over the 0.0227 they had me figure out a bit ago. And that comes out to be 0.00867 quantity squared divided by 0.0227, and that's 0.0033. And if we want to put that in scientific notation, you don't have to. You can leave it just like it is, though. 3.3 times 10 to the minus 3. And I have a whole bunch of sig figs and not a lot of my k. Why did I do that? 3 sig figs. I think I'm going to go with 3 sig figs. So I'm going to add a 1. All right, now I'm looking at my key, and I have 0.0266 in the denominator, so I may have made a little arithmetic error somewhere along the way. If you've worked this and you have 0.0266 in your denominator right here on this k expression, I got that the first time I worked it. Could be a rounding error somewhere, but I still got 0.0087 up here, 0.0227. I may have looked at something wrong, but anyway, I may have done it wrong the first time. So in any event, you may have gotten 3.33 times 10 to the minus 3. Big whoop. You're still going to get your points. That was 3 points, by the way. A point for the correct value here. A point for the fact that these two are equal to each other. So however you communicated it, I communicated it right there. But the fact that x equals x, that this concentration is equal to that concentration somewhere on your paper. And then a point for the final answer, which I should have boxed. And the final thing they want is for us to calculate the mole fraction of F2 in the container. So we're back to pity points. But I don't know how you could have gotten there if you hadn't have done the equilibrium piece. So the moles of ASF5, the moles of ASF3, which are also the moles of F2, are what I need in order to be able to do this. And so what is this molarity? 0.0227 times the 10.5 liters of the container will get me to moles, because this is moles per liter. So my liters will cancel and I'll have moles. So 0.0227 times 10.5 gives me, and again, I may have an arithmetic error somewhere in that 0.227, but this should come out 0.238. I think we're agreeing somewhat. And this would be the 0.0087. Times the 10.5 liters. I didn't write my half up there earlier. I put a decimal, but I didn't write the half. 0.00867 times 10.5. And I get 0.0910. So therefore, the mole fraction of F2. So that is the mole fraction of F2 equals the moles of F2, 0.0910. And don't forget that you add that right in here. Do it right now. Do not wait. Don't forget. This is the most common mistake. Kids forget to add that number of moles back into the total. So you use that number twice. It feels weird, but you do it. And then its partner, 0.0910 as well. And then the 0.227. No, 0.238, sorry. 0.238. This number. Okay, so let's see what that comes out to be. I'll clear this mess out. 0.091 divided by parentheses 0.091 twice plus 0.238 equals. Therefore, the mole fraction of F2 is equal to 0.217. Okay, arithmetic error or not, that's the answer I got the first time, so I think I'm correct. All right, was that our last one? Could we be so lucky? Oh no, there's one more. All right, one more. Are you up for it? One more. This is a good one too. And the reason it's a good one is it's number one from last year, from 2010, the 2010 exam, and you're probably preparing for at least the 2011 exam, if not beyond. And so it's more recent, so you can kind of get a feel for how these looked. But let me, having said that, give you the other caveat, which is it's a B question. And they're always just a little bit off the beaten path because the best question was used on the operational exam. So sometimes this one is like the B team question, is what I've always explained to students. Let's go back to 100%. See if I can fit all this on here. Okay, it's going to be a bit before I need my calculator, so I'm going to minimize it and make this bigger so you can see better because I got to do some drawing and stuff. We'll need more room. All right, the compound butane, C4H10, occurs in two isomeric forms. Isomer, iso, prefix meaning same, mer meaning form. So we're talking same chemical formula, C4H10, different arrangement of the atoms. So it forms normal butane, which is the 4 in a row carbons with saturated with hydrogen, so carbons making 4 bonds at all times, and isobutane, which, if you know how to do the organic nomenclature, it's telling you there's a methyl group hanging off of the number 2 carbon, and prop means 3 carbons, ane means all singly bound. Probably need a video on that, huh? Hopefully you got that in first year. That's really a first year concept. Hoping that when you did nomenclature, you did some nomenclatures of alkanes, alkenes, alkynes. If you've ever heard of laying the foundation, it's a great laying the foundation lesson. Ask your teacher for it, because they may not have gotten trained yet. They may have the book and not know that nomenclature lesson's in there, and that piece of it's really good for you to do. All right, so both compounds exist as gases at 25 degrees Celsius. I'm going to do that just in case I need it, and that is what temperature would equal, and then here's what pressure would equal, because I feel a Pivnert coming on. Draw the structural formula of each of the isomers. Include all atoms. They weren't kidding about that. Include all atoms. Clearly label each structure. Okay, that's pretty clear directions. Here comes normal. String those 4 carbons. 1, 2, 3. I'm making sure each carbon has 4 bonds, and I put an H on each one. Isn't this fun? And there you go, normal butane. Versus 3 carbons in a row, that's what prop means. The 4th carbon, I can go up the page or down the page. I'm going to go up the page. Doesn't really matter. What matters is it's hanging off the number 2 carbon. So I would number this chain of carbons right here, starting at either end because my branch is in the middle. But if you always start numbering at the end closest to the branch, so the branch holds the smallest number possible. There's a whole bunch of rules for this. So either way, whether I come at it from the left or the right, that's my number 2 carbon. So that is not a 2 as in diatomic. That is a 2 as in the number 2 carbon. So my methyl group, which is 1 carbon, that's 1 carbon, total of 4, works that way. All right, so let me clean up my drawing just a little bit. That was pretty good erasing on my part. All right, so every carbon has 4 bonds. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so this is my isobutane. Not improper if you named it 2-methylpropane. On the basis of molecular structure, identify the isomer that has the higher boiling point. Well, that's a very bizarre question in the middle of an equilibrium question. But okay, I'll humor you. We are now journeying over into land of intermolecular forces. Well, you can imagine these branches change the shape of the molecule. And if you actually built this with the little ball and stick models your teacher probably has, you'll see that this does not make the long, elegant chain of carbons that go ziggy-zaggy with the 109-degree bond angle going on. But this becomes more of like, I'm not going to say a sphere, but it becomes more balled up. It definitely reduces its surface area. So when you reduce that surface area, you don't get as much contact between these hydrogens that are surrounding all these carbons. So you don't get as much intermolecular force. You don't get as much induced dipole attraction. So now I got to kind of, now that I've thought that through, I got to sort of put that into words for you. So my choice is the correct choice, which is the normal stretched out butane, because I'm going to basically get more surface area contact between molecules in a sample of nothing but this normal butane compared to what I get in terms of isobutane if I had a sample of it isolated. So the N-butane isomer is my answer. On the basis of molecular structure, identify the isomer that has the higher boiling point. Okay, I've done that. The N-butane isomer. Since its linear structure allows neighboring N-butane molecules to approach one another more closely, to snuggle up together. No, don't write that. To approach one another more closely is probably the way to go. Think three-dimensional. If they're linear, they can approach each other from the top of the page, the bottom of the page, the floating above the page, and going behind the page. If they're more balled up, then they aren't going to get near as much contact as if they were like rods. Think about maybe putting a bunch of jawbreakers in a jar versus putting a bunch of Twizzlers in a jar. The Twizzlers are going to be able to be in contact with each other a lot more due to their shape than the spheres that would be the jawbreakers. And I'm not saying it's an actual sphere. I'm just saying it's more spherical than it is linear. All right, so they can approach each other more closely. What does that mean? That means that we have more temporary dipoles, induced dipoles. You choose your language. The translation on that, if you have not done intermolecular forces yet, you missed this question, and there's no shame in that because you haven't learned that yet. But induced dipoles happen in any molecule, in all molecules, when they interact with each other because electrons repel each other. So when one molecule approaches another, there's some electron movement going on there, and spontaneously one critter in the pile may have its electrons piled up like a traffic jam on one side of the molecule, which is going to set off a chain reaction in all of its neighbors, which is going to repel their electrons away from that traffic jammed area, but attract on the other side of the molecule and a different neighbor their electrons to the side that doesn't have a lot of electrons they're repelling because they're in the traffic jam. That's going to become way better and way, way more clear when I actually do the recordings on the IMFs. I have a LiveScribe out there now if you want to go and investigate this concept, but that's completely up to you. It doesn't have anything really to do with equilibrium, but this is the way modern questions are. They weave various parts of the course into what you are not expecting to happen, like in question 1, when you're supposed to be doing equilibrium, and now here you are doing IMFs. So more induced temporary dipoles form between N-butane molecules. So what? Therefore, more energy is required to overcome N-butanes. There's lots of names for this. I'm going to use LDFs, London dispersion forces. Goes by 3 names because you know grown-ups can't get along. You've learned this lesson by now. London dispersion forces, LDFs, and you too can use that abbreviation. London dispersion forces, induced dipole, or just plain dispersion forces. To overcome those London dispersion forces than those of isobutane. Okay, so if you missed that point, let it go. At this point in the year, if you're following the NIMSY sequence, I wouldn't expect you to know that. If you've already done intermolecular forces, then you probably did get it right. Alright, so now the 2 isomers exist in equilibrium as represented by the equation below, where they gave me a Kc. Pay attention to that. They're both gases. 1 mole on the left, 1 mole on the right. Delta N is equal to 0, so Kp equals Kc. And I'm going to put that at 298 Kelvin. And I've got other volume stuff, I think, back up here at the beginning. Nope, just a pressure, 1 atmosphere. Alright, so I have a molage. Suppose that 0.01 mole sample of pure N-butane is placed in an evacuated 1.0 liter rigid container. There's my volume. At 298 Kelvin. One more time. Write the expression for the equilibrium constant Kc for the reaction. Since they put the C, that means you're in the land of square brackets. Let's see if I can write the word isobutane. Over N-butane. In nice little square brackets. You actually get a point for that. Alright, then calculate the initial pressure in the container when the N-butane is first introduced, in other words, before the reaction starts. So here's your Pivnert moment. I hope you've come to expect them. This is, if you have, then I have already succeeded in moving you away from the defenseless student into the aggressive student. Bring it on. Bring on the Pivnert. 0.010 moles are 298 Kelvin divided by a 1 liter container, which was cheesy. Okay, I said it would be a while before I needed my calculator, so now I'm going to shift to this view. Therefore, P equals 0.01 times alpha R times 298. Get my numerator. Divided by 1. So I don't even need to do that. I wish I hadn't punched that button now. So pressure is going to be, how many sig figs do I need here? Let's go with 2. Why am I going with 2? Because 2.5 on the Kc. No, this is 2 right here. That 0 is not significant. It's a placeholder. Alright, so that comes out to be 0.24 atmospheres. Alright, so that was N-butane before anything really happened, just the initial pressure. So if I need that in a rice table later, I got my I. Alright, so the N-butane reacts until equilibrium has been established. Uh-oh, here it comes. Calculate the total pressure in the container at equilibrium. Alright, at this point, the N-butane reacts until equilibrium has been established. Calculate the total pressure in the container at equilibrium. Well, the pressure is the same. So the total pressure remains exactly the same as the initial pressure because it's a 1-to-1 stoichiometry. So the total pressure remains the same. And they did say calculate, so you better put a number in here. since the number of molecules in the container does not change. Due to the 1 mole to 1 mole ratio. Now, if you need proof, we can do the proof. You can do the proof, and I'll do it for you, but it's not at all necessary, and you'd have been kind of frustrated with yourself by the time you got through. So we're back to learning what's going on conceptually. N-butane with isobutane. You do not need this, okay? This is me proving to you that it really was that simple an answer. 0.24 and nothing. So for every one of these N-butanes that decomposes, I make an isobutane. It's a one-to-one thing. Pressure is simply the number of molecules that are colliding with the container. All right, if it's all at the same temperature, that means they all have the same average kinetic energy. So their energy with which they collide is held constant. So if I lose some, I gain some. Either way, I'm still in equilibrium. That same pressure, the same number of molecules hitting the side of the container, even though their identities have changed. So the change is lose some, make some. And that means that E is 0.24 minus X, E in terms of X I should say, and 0 plus X is X. We'll get to E in a minute. In the meantime, let's do K. We just found that K was, they told us, right, 2.5 somewhere? Yeah, right here. K is 2.5. I also know that Kp equals Kc because there's no change in the number of moles. So even though I'm doing a Kc, it's okay to talk pressure because they're the same. Well, let's talk pressure because that's what they're asking me about. So like I say, they're the same. So it's 2.5. And that's equal to X over 0.24 minus X. So cross multiply 2.5 times 0.24. And that is 0.6. That's a nice number to deal with. So 0.6 minus 2.5x, I'm just cross multiplying across this expression, is equal to x. Collect like terms. I would add 2.5x over on this side to get 3.5x equals 0.6, but I'm going to write it this way. You don't have to. This is the way I like it. So let's solve for x. What would that be? 0.6 that's sitting in my calculator divided by 3.5. And that is 0.17 atmospheres. All right, so now I come over here and I go, that's 0.17. And this would be 0.24 minus 0.17. And that comes out to be 0.07 atmospheres. Atmospheres. What's the sum of the total pressure in the container? Does that look familiar? So if you did all that math, you still get your points. You just spent a lot of time doing something you didn't have to do. So I know it said calculate, which is kind of mean because you really didn't have to calculate. And when I looked up the grading standard on this, they didn't calculate on the standard. They just wrote basically what I wrote, that the pressure remains the same because of the 1-to-1 ratio. 1 mole of reactant is still making 1 mole of product, and the number of molecules is constant, so the pressure remains constant. But if you did all the math, it's okay. It's good practice. All right, then calculate the molar concentration of each species at equilibrium. Okay, well now we're doing molarity, so this gets a little bit different. So, give myself a lot more room and a new color. Let's go back and read again. What do I have here? I have, there, I'm back up at suppose. Suppose that 0.01 mole is in a 1 liter container, so the molarity is 0.01. All right, now I'm ready. Let's rice this baby again. For real this time. 0.01 molar. None. Minus x plus x. x. 0.01 minus x. X. E. K equals. Still 2.5. Remember Kp equals Kc? Change the number of moles here is nothing. So K equals 2.5, which equals x over 0.01 minus x. What I was saying earlier is that you don't have to write a rice table. If you just realize that this is the pattern you've been following through umpteen problems, it's okay to start here. Especially in the later parts of the problem like this, we've already written the K expression and gotten your point for that. So the rice is not necessary. So when I cross multiply 2.5 by 0.01, I move the decimal twice. So that is 0.025 minus 2.5 x equals x. Collect like terms. 3.5 x equals 0.025. So x equals 0.025 divided by 3.5. And that is 0.007. I wonder if sometimes they do that on purpose. Bond, James Bond. All right, 0.0071 to have two sig figs. And so let's use those properly. So this is 0.0071 molar, and this will be 0.01 minus that number, 0.00286, 2 sig figs, 0.0029. That's supposed to be a therefore, and that doesn't look very much therefore-ish, does it? There we go. All right. And then the final question, oh, maybe it's not the final question. And this is a marathon. All right, so if the volume of the system is reduced to half of its original volume, what will be the new concentration of N-butane after equilibrium has been reestablished at 25 degrees Celsius? Okay, so dang your hide, you're going to cut my volume in half. I'm working in Kc, so if you cut my volume in half, it's twice as concentrated. So which critter am I talking about? N-butane. And N-butane is this one. So 0.0029 doubled. So 0.0029 times 2. Number sitting in my calculator. 0.0057. All right, twice as much is the answer. .0057 molar, or you can put it in scientific notation. But you better not just do that. You better put, if you're going to, I mean, if you could just reason with it, you need to just still write a sentence. Just for good form. Decreasing the volume of the container. It says justify your answer. Volume of the container increases pressure, but there are the same number of moles of gas on each side of the reaction. There is no shift in equilibrium. However, having, I've never known exactly how to pronounce that, but I am from Texas, so you have to forgive me. Kind of a hick. The volume doubles the concentration. The truth is, you only need this part to get your credit. I wrote the rest, so if you look at this later and you study this later, it may make more sense to you. That this question was not asking about pressure, even though they did the whole trick of, I'm going to reduce the size of the container, I'm going to squish the system. Well, there's a mole on each side. Squishing doesn't help. It doesn't favor one side or the other, but that's not what they asked. They didn't ask about the pressure. They asked, what will be the new concentration? So if you decrease the volume, then you're going to, especially by half, you're going to double the concentration because it's a molarity calculation, moles per liter. So you're going to be dividing by half as much, which is the same thing as multiplying by 2. All right, so finally, it really is finally this time. Suppose that in another experiment, a 0.01 molar sample of pure isobutane. Wait a minute. This suppose was 0.01 molar. That suppose is 0.01 molar. This was N-butane. Now they're going to do the same thing with isobutane. Calculate the molar concentration of each species after equilibrium has been established. It's the same calculations. The only difference is, in your Rice table, this would have been a minus x over here, and this would have been a plus x. But you're just going to swap these two concentrations, and there's no difference here. The concentration is going to be the same. It's going to be exactly the same. It's going to reach equilibrium. So the ratio, K, never forget, is a ratio of products over reactants and is temperature dependent. Therefore, the concentrations of isobutane and N-butane at 25 degrees Celsius, or 298 Kelvin, the concentrations are, subject-verb agreement, are the same as above. So, isobutane is 7.1 times 10 to the minus 3 molar, and N-butane, somehow I got 8 off of that, is 2.9 times 10 to the minus 3 molar. Because they've got to maintain that same ratio. They're at the same temperature. All right. You're done. Yay! Yippee skippy. Happy dance time. Thank you so much for joining me. I hope you're finding these useful. I hope your scores are improving and that you've gathered loads of college credit for your efforts, especially if you're stuck listening to me. Thanks so much. Have a great rest of your day.